take a look at section 5.2. So we're going to look at kinetic and potential energy here.
Wow. I just had both.
There are 3 objectives. First, identify and calculate the different forms of energy. So forms meaning potential, kinetic, chemical, internal types of energy like that. Second, we're going to look at what's called the work kinetic energy theorem. And third, we're going to classify and solve problems with different types of potential energy. So you've heard these terms in your basic science courses, but we're going to go into a lot more detail as to what they are and how they're used. The first example here, kinetic energy. Okay, is the energy of an object's motion. That's really all it is. The energy of an object's motion. Now, the interesting thing to think about is the following. Even though I'm standing still at rest, okay, we would say like my kinetic energy as a body would be 0 because I'm not moving. But realistically, everything is moving. Okay, because what is temperature defined as? Anybody know what temperature from chemistry, the definition is? You can, as a do with transferring energy. It's not defined as a transfer of energy.
Is it like the speed, like particles moving around?
Yeah, it's the average kinetic energy of the particles or the speed of the particles. That's what it is. So something that is hotter in temperature or higher in temperature has more vibrations of the molecules or is moving faster. So although on a macroscopic level, a person standing still would be a person with 0 kinetic energy, a person that's standing still technically has some kinetic energy in their molecules. And if you had no energy, you wouldn't be a being, right? But we start talking about that, we talk about internal energy. Okay, internal energy. But the idea for kinetic energy, when we're looking on a macroscopic physics level, has to do with objects in motion. Not molecules really we're looking at anymore, okay? That would be more stuff that you would look at if you became, say you became a materials scientist, or a materials engineer, or a chemical engineer. You would look at kinetic energy of molecules on subatomic levels, which would be very different. Okay, you'd be looking at the energy of an individual molecule, maybe. Toward the end of the year, we're going to look at energy levels of emissions of radiation. That has to do with identifying what type of a particle it is. But again, this is kinetic energy of an object moving at a macroscopic level. What does that mean? Macroscopic?
Smaller than macroscopic? Bigger than macroscopic.
Yeah, all the way around. So something on a macro level means on like a large level, large scale. So macroeconomics versus microeconomics. Okay, macroeconomics is looking at like the global economics of the whole world. So, you know, for example, microeconomics might be looking at the economics of a company. So you're looking at their financials. What has to do with their company, their profit, their loss? Micro versus macro. So on a macroscopic level, kinetic energy has to do with objects' motion. Now, from last section, what were my units for work? What were my units for work?
It was,
Tristan?
The forces times resistance times cosine theta.
Okay, and the units, Tristan, were?
It was joule because it was mass times.
It was force times
Force times mass.
times distance.
Yeah.
So it was joules for work last time. Let's take a look at these units now. The units of mass are what? Look at the unit. 1/2 has no units. What are the units of m for mass? Kilograms.
Why does it change? Like one thing is mass, one thing is like grams, and the other is kilograms.
The base unit for mass is always kilograms, we said. It's the only one that has a prefix on it. So like the base unit for distance is meters. The base unit for time is seconds. The base unit for mass is kilograms.
So on the homework, there was one where you like it was given, it was kilometers, and you had to transfer it to
Meters. Yeah. So the units for velocity.
Meters per second.
Meters per second.
Squared.
No, just meters per second. And that unit is squared. That unit is squared because, yeah, exactly. Because V is squared in the formula. So the question becomes, how does this become a joule? How does this become a joule? Is this really the same thing as down here? Well, let's break up a Newton into what a Newton is. What's a Newton?
It's kg mt l.
Yeah, kg m per second squared. Good. So this is what a Newton is. You guys got to take a look at your units and remember, we go over these every class for a reason. Okay, whenever I give you a formula, always go look at the units. Take a look here at the bottom. This would become kilogram, then there would be a meter times a meter, meter squared, and second squared. Same thing we have up here. Exact same units as we had for work. Again, at the bottom here you can see your units. A Newton is really a kilogram meter per second squared. So these units at the bottom right here end up being the exact same thing as these units up here. Okay, so the units for energy are going to be the same as the units we had for work. So joules are our units. Okay, joules are the units for energy. Okay? Is that funny for some reason? Okay.
What are you watching?
I'm very, what? I'm trying to, I like jokes, so please tell me if something's funny. Let's take a look at example one. Well, I mean, let's take a look at example one. Appropriately funny. I should censor myself at that statement.
How am I supposed to know that?
So a 12 kilogram bowling ball moves at 3 meters per second. How fast must a 4.5 gram bouncy ball, like those Super Bowl, you know, you bounce them, the ones that are like you can sit there and bounce all day long and they lose very little energy? Okay? Now, how fast must that move for them to have the same kinetic energy? Please list your givens. List your givens. List your givens. Come on, let's go. Use your units to help you, please. Use your units to help you, please.
M equals 12 kg.
You're on this slide, and you should be editing, not in your browser. Open Notability, edit.
So I have to like read down.
I told him to put a reminder.
Yeah, I got a reminder.
You need to put a lock on your iPad so people don't mess around with your iPad. Simple, Gio.
Yeah.
So you change the password. Don't tell anybody, Gio.
Password is 6969.
Come on. M1. M1.
I don't even know. You ran.
It's just no my pen, I got it.
What's the first mass?
12 kg. Bang.
Luke, you're way over the line now. Stop. The second part that we know that the 12 kilogram bowling ball moves at 3 meters per second. Even if it doesn't use any words there, use your units. 3 meters per second means it's what? Good, Nina. Velocity. V1 is 3 meters per second. So that's the first object. The second object has a mass of 4.5 grams. What should I do with that? James?
Change it to 0.0045 kg.
Convert to my base unit of kg, 0.0045. James remembers that kilo is 3 times or 10 to the third bigger, or 3 decimal spots motion. So move it 3 decimal spots. What are we trying to figure out?
V2.
Yeah, it says how, let's see, where are we at? How fast must a 4.5 gram bouncy ball travel? So V2 is the question.
So do you first have to find the kinetic energy?
So there are 2 ways to do this problem. One way that Luke just mentioned is to find the KE of the first object. And you would have 1/2 times 12 times 3 squared. So 6 times 9 is 54. Okay, so you could do that. Or you could set up equations and set them equal to each other. Guys, relax. Relax. So option 1, we're going to do it both ways. And then option 2. Option 1 is to find the KE of the first scenario. So you could say, all right, the KE of the first scenario is 1/2 mv squared. And I'm using the ones because it's the first scenario. Plugging in our numbers, we have 1/2 times 12 times 3 squared, which is indeed 54 joules. So that's one way to do this, to finding the kinetic energy of the first object by itself. Then we could say, well, the kinetic energy of the second object is the same, which is given to us. So we could say that KE2, 1/2 m2 v2 squared. But we know that that's equal to 54, right? Again, the kinetic energies need to be the same. So we could set this second equation equal to 54 instead of KE2. So go ahead and do this. Erase your KE2 down here and put a 54 in its place. Yes? And you could solve generically for V, but in example 2, I'm going to do a completely generic solution. So I'm just doing it with numbers first. Okay, so in the first example, the first way to do this is to find the KE of the bowling ball, 54 joules. Then go ahead and find or set that equal to the KE of the bouncy ball, and you could solve for V2 in this problem. So you could plug in your mass and solve for V2.
Is it just the velocity that's being squared? Or is it
Yes.
the whole part?
This is like this. Okay, does that help? So we have 54 times 2 to get rid of the 1/2, divided by m2 equals v2 squared. Again, how to get rid of 1/2, you multiply by 2. That's 54 times 2. Divide by m2 to get rid of it, leaving you v2 squared. So take the square root at the end to get rid of this squared over here. That'll give us the velocity for the second object. What do you get for the second object's velocity? Anybody got a number for me? James?
109.54 meters per second.
100 and...
9.
I got something different. Can I just get a check? Can I get a check?
I got 154.9.
Check your numbers real quick. Yeah, see if there was a miscalculation. Should be around 155. Okay, and that makes sense because obviously it's going to be greater than the other one, right? A bowling ball tossed with a certain velocity and a little bouncy ball tossed with a velocity. For the energies to be the same, that bouncy ball has got to be going, oh, God bless you, a lot faster. So the velocity of the bowling ball is only 3 meters per second. The answer that we get here is around 155. Okay, around 155.
So is it like, is the system that's having a leaking period?
154.9?
Yeah, 154.9 is the exact number. Not really, Tristan. Don't confuse the two. So that's one way to do this. Who could think of a second way to do this problem that we don't need to even find out 54 joules as our answer for the first part? How can we do this problem without even determining the number 54? Without even using any numbers in the beginning at all?
You can just make the two equations equal to each other.
Yeah, so the kinetic energy for one object is 1/2 m1 v1 squared. The kinetic energy for the other object is 1/2 m2 v2 squared. Those are the energies of each object. Since they're the same in this problem, we're told that the energies are the same. Set those two equations equal to each other. So what Aaron is saying to do is the following. Aaron is saying, let's do this.
Okay.
And that makes a little bit more sense for simplicity. You know the energies of the two particles are identical, so set their energies equal to each other. M1, V1 refers to the bowling ball. M2, V2 refers to the bouncy ball. What happens to the 1/2s that are on both sides? Yeah, they cancel. Remember, same thing on both sides, cancel. Which results in a pretty simple equation. And instead of solving this the other way we did it in method 1, now we can just isolate V2. We can simply isolate V2. I'll leave the first answer up. So divide by M2. Okay, that's where we're at right now. So we divide by M2, then take the square root. And the answer you're going to get from this, so let's take the square root, which gets rid of the square here. And that answer, m1 v1 squared over m2, the square root of that, will give you 154.9. Okay, this is a complete algebraic solution as opposed to plugging in numbers and then setting the equal energies, or the energies equal to one another. I would recommend that if you're ever given a problem where you're told the kinetic energy of one object is the same as the other, set them equal to each other like this, just to start the problem. And it makes it a lot easier. 1/2s cancel, solve for V2, you're done. Okay, just plug in numbers at this point.
Well, I like the first one.
That's fine. You can do this method either way. That's absolutely fine. Okay? Absolutely. Doesn't matter. Now, the only issue you're going to have, Luke, is this. If I said the mass of object 1 is triple the mass of object 2, now you don't have numbers for mass. So in place of m2, you have to put 3m1, showing that it's triple m1, and then the m1s would cancel. So imagine the example said that the mass of the second object is triple the mass of the first object. Completely different example, right? But then you would replace m2 with 3m1, and the m1s would drop off. So if you don't have a mass in the problem, if you're missing something, you may have to solve generically. Okay? You may have to solve generically. But the idea that each one of these works is fine. Okay? Go ahead and plug in here. You'll get the same number, 154.9.
That's all I got.
And the units are meters per second still. Okay, still meters per second. This is a pretty basic example for kinetic energy. Okay, just to give you a heads up. This would be a very basic example for kinetic energy. Two objects with the same energy, set them equal to each other, solve for what you're missing. How could I vary this problem? How could I vary this on a test? This is the stuff you need to think about, and I notice some of you might not be always thinking about this. How would I vary this on a test? Okay, change the mass, so change the numbers around. Good. What else?
You can give the object's velocity and leave out
Exactly. Leave out
mass.
Yes. Leave out the mass. Sorry. So maybe you're given the fact that you laughed made me laugh, or else I wouldn't laugh. Just so you know.
I love your smile.
You could be given the velocities and be asked to find the mass, right? So it could vary. Could vary. Let's take a look at our next thing. The next topic is our work kinetic energy theorem. I'm going to go through a quick derivation of where this comes from, but the conclusion is what's important. So if you want to sit back and watch for a little, that's fine. Okay, you don't have to actually write everything down. The conclusion at the end is what's really important, but if you watch, maybe it would help you understand where it comes from. So the idea is the following. First, the amount of work on an object, remember, is the force you put over a certain distance. Remember FD cosine theta from last class. So if I push with a certain force over a certain distance, I'm giving the object some energy. That's what I'm doing really. I'm providing this chair with some energy by dragging it. It currently has no kinetic energy, right? It's sitting still. But as soon as I apply a force, I'm doing work on the object, and since it's now moving, I'm giving it kinetic energy. So there exists a relationship between work and kinetic energy. And that's what we're going to come up with right now, which is entitled the work kinetic energy theorem. And what I want to do is start with our equation for work. So we're going to start and think about our equation for work. What was that from yesterday? The equation for work. Or last week, rather. Work equals what? F. You're close. FD is a good start. What else?
Cosine theta.
Yeah, cosine theta. That was our work equation. Our work equation. Now, let's say we're looking at just linear motion, because we're not going to be looking at two-dimensional motion for kinetic energy work theorem. So just linear motion. What would theta become?
180. I mean,
Well, okay, that's a. But I'm providing a push. We're not looking at friction.
1. Cosine theta would be negative 1.
Cosine theta would be 1, but what's theta is the question. If I push this way, okay, and the object is moving this way, what's the angle between these two vectors? So I'm pushing to the right,
0.
okay? It's 0 degrees, right? Because you're not moving. Like, if I were pushing to the right, or if I were pushing in this direction, like I was pulling on an object, but it was moving to the right, there would be an angle between the pull and the motion. But I'm pushing completely horizontally, and it's moving completely horizontally. So in this case, theta is going to be 0, and therefore cosine theta is just 1. Okay, if you remember from last class, the cosine of 0 is 1. So for this equation, what we can do is we can start by saying, well, you know what, there's not going to be a cosine theta. So we can say that this is simply just going to be work is equal to FD. But what is the net force on an object defined as from Newton's second law? The net force, because we're looking at the overall force here to the right. What is the net force equal to? Newton's second law. F equals? Yeah, ma, good. At mass times acceleration. So let's replace this force with ma. And this is what a derivation is, by the way. I'm showing where it comes from. Again, you're not going to be responsible for recreating this at all. So we know now that we have ma times the quantity d. Okay, ma times the quantity d. And what I'm going to do is I'm going to rewrite this. I'm going to group it. I'm going to write it like this instead. And I can do that. Why can I do that mathematically? Who remembers? Yeah, and in this case associative, right? Grouping. But the idea is right, yeah. You can multiply in any order. So I could group A and D together because of the associative property of multiplication. Now, I'm going to pause for a second there and come back to this equation in a sec. Okay, I'm going to slide down and we're going to come right back up to here. So let's just put a little line there for now. If you remember our equation of motion from kinematics, what was the equation that had squared terms in it? There was only one that had squared terms in it. It was like VF squared. Go ahead. VF squared equals?
VF squared equals VI squared plus 1/2 plus T
Guys,
plus T
let the person raise his hand answer because he's hearing all you and confused.
plus T
Not T.
plus A.
Okay, now we're guessing.
Yeah, I remember.
Who has more?
1/2 AD squared.
That's the other one.
A.
It's on your formula sheet if you just look it up for now. You can do that.
Is it AX?
It's close to AX. Not AT. That's the other one. Tristan? 2AX. That was our equation of motion from kinematics where we related our square of our final velocity and our initial velocity. Now, in these problems, we've been talking about distance. This has displacement. So if I'm pushing an object though, again, I'm pushing an object in one direction, I'm adding some velocity to it. In only one direction. So what does that mean about my displacement and my distance? I push this desk, okay? 5 meters that way. What's the displacement? What's the distance? So what can you say about the distance and displacement? They're the same when I push in one direction. So for these problems, see how we have the 2AX there? Think of the X as D instead. And it'll make sense in a moment. So put a D here in your mind. Now, look back up here. See how we have AD here? And there's an AD here. Okay? So let's solve for the AD in this equation down here. Let's solve for the AD. What would it look like when solved for AD?
When solved, it would be VF minus VI divided by 2.
Don't forget your squareds, right?
What? Oh yes, and squared.
All right. So that's what AD would be when you solve for it in this equation. So we could technically take this expression right here and do what with it?
Plug it into
Substitute.
Yeah, substitute it. We could substitute this in up here. And does anybody notice something already that's happening? We have mass. We have velocity squared. It's divided by 2. What does that make you think of?
the equation.
Which one?
The first one.
This one, the one that says 1/2 MIVI2.
Yeah, it has to do with like kinetic energy that we just did. Take this and plug it in up there and see what you get for work. So this is all work. Remember, we're looking at our work kinetic energy theorem. So at the bottom line, we'll write down work is equal to, it's going to be mass from right here, the mass, and then we'll plug this expression in right here for AD.
Does it stay in parentheses so you get it first? And then
I'm going to leave it in parentheses for now, yes. Okay, that's what it would become. Again, if we take this expression here and replace AD with that expression. Now, look at this at the bottom here. At the bottom, really all it is the following. Distribute the M. Okay, and if I think about this as dividing by 2, I could say I could just make it a 1/2. Everybody agree with me on that? Right? When you divide by 2, it's the same thing as multiplying by 1/2. So we can bring out a 1/2 instead and write it like this. It's the exact same thing. Half of that quantity, or taking that quantity and dividing by 2. They're identical to one another. So this is just kinetic energies. And our final line looks like this, and this is what you need to remember. So our final line has 1/2 mvf squared minus 1/2 mvi squared. Well, 1/2 mv squared is kinetic energy. So how would you say, or what would you say this is really? How would you put this into words? The work on an object is equal to what? The work on an object is equal to what? Take a moment to think about it. What is the work on an object equal to? How would you say this in words? Without equations, what would you say? What does 1/2 mvf squared really mean?
Half of the final velocity.
The mass.
Yes, that's translating the variable for sure. But I want to know, like, in terms of what we've been talking about, kinetic energy. How would I make a kinetic energy work relationship out of this?
I would say the difference in velocity.
Close, that's the closest so far. It's not the difference in the velocities.
Is it like, it's kinetic energy final minus kinetic energy initial?
Yeah, that's exactly right. I heard Julian say that. Yeah. The difference in the kinetic energies is what's going on here. So take a look at this last line. If I said to you, find the kinetic energy of an object, you would use 1/2 mv squared, the equation we just used a minute ago. But because there's a VF, and because there's a VI now as subscripts, we know that that's the kinetic energy final and the kinetic energy initial. So the work kinetic energy theorem is in that box right there. But if you want to write it like this instead, to make it easier for you to see, it would look like the following. And when you have final minus initial, it's just delta. So this, in essence, is the work kinetic energy theorem. And I think if you look, can somebody pull up the formula sheet, please? Tell me what I wrote down on there. I think I wrote down what's circled. I think that's what I give you at the bottom there.
What's the little underline in the
On the what?
under the KF?
Is that better?
The underline.
Who's got the formula sheet up?
Me.
Can you tell me, Lisa? Is this what I gave you in the circle here?
Okay, got it.
Yes, you did. You did.
Yeah? All right, so, listen,
You're on Google Translate.
the theory is the following. The amount of work done on an object, is equal to its change in kinetic energy. Its change in kinetic energy. Okay, so I'll give you what's circled here at the bottom. But again, this is useless unless you know what to do with it. So you need to be able to remember that this really means this, but that really means that.
So you can just say the bottom one.
Okay? Sure, absolutely. Absolutely. Okay? No. You know, listen, you're going to be given kinetic energy as a formula. You'll be given KE equals 1/2 mv squared. So when I tell you that work equals the change in kinetic energy, you should be able to come up with this just by saying, well, delta KE is change, which is final minus initial. Well, final kinetic energy is just 1/2 mv final squared. Initial kinetic energy is 1/2 mv initial squared. James.
What if the F and VI are both 0?
Then is there any change in kinetic energy? So is there any net work done?
Right, but like, what if in between those two, like, 0 velocities, it was moved? Like, is that not counted as work?
So for example, I push an object, right?
Yeah.
And what happens? It slows down and comes to rest?
Yeah, well, like you push an object and then you stop pushing it, like in between.
So what stops it from moving?
Friction.
Okay, well this isn't involving friction. Okay, this is not incorporating friction here.
Right.
Okay, the minute friction is involved, the problem will change a little bit. We'll see that. This is the work kinetic energy theorem for just general Newtonian physics.
So you're assuming that will just continue forever because there's no friction.
What we're assuming is that the work done on this object, remember work is Ft cosine theta, F is the net force. The net force. So if I'm pushing with 20 newtons and friction is pushing back with 8 newtons, I'm looking at using an F value of 12 there. Okay? So it's already incorporating friction. Sure, if you push an object and then stop and then it comes to rest, yeah, over time it'll come to rest because of Q loss or energy loss to friction.
Right, what I'm saying is like, if I like push this across the desk and I take the VI and the VF, they're both 0, so everything in here is 0, but I still pushed it, is that what?
But remember, we're solving for the net work done. The work done by friction cancels the work you do, giving us 0 as a value. That's what I'm trying to say. So yeah, sure, you're doing work, but the net work on the body is 0 because the work of friction is negative. Remember cosine 180? Okay. Good question. Very good question. Let's look at example 2 now. Theorem in example 2. Example 2. Can I get somebody to read this, please? Can I get someone to read this, please, Teresa?
On a wood floor, you decide to slide around when you're just put on a new pair of socks. Your mass is 50 grams, and you run and start to slide with an initial speed of 1.5 meters per second. How far will you move if the coefficient of kinetic friction between your socks and the floor is 0.75?
Okay, so there's a lot going on in this problem. Let's list our givens, please. Let's list our givens to start.
Mass is 50 kilograms. VI equals 1.5. And VF equals 0, right? And then mu equals 0.25. And yeah.
I think that's it, right? Okay. What are we trying to find? How far will you move? Okay, a lot of you are having struggles in your test, just listing givens. Okay, so you need to do this when we do it in class. You can't just say, I'm going to let somebody else do it. When I say list the givens, it doesn't mean wait for Lou to answer with all the givens.
Okay. Thank you, Lisa. Whatever.
Just not try.
I'm trying though. That's the thing. I'm trying. It's just unsuccessful every time. Like, you would think the odds would be in my favor one day, right?
The odds are always
The odds are never in my favor.
Yes, they are.
So the idea for these problems, guys, again,
I traveled 500 miles to get
is that we need to start by listing the givens. How? After this, we have to start asking ourselves, well, what's actually going on in this problem? Okay, you're running. You're then going to slide on your socks and like kind of coast for a little while and come to rest. So what is doing work on your body in this problem? What is doing work on your feet in a sense? What is it? Friction. Friction is doing work, right? Again, you are running. You're running with a speed of 1.5 meters per second. You then slide, so you like come to like a sliding stop, and your body's going to slide a little bit, a certain distance, but it will stop because of friction. So friction is doing work. Now, let's start by listing our work kinetic energy theorem. Yeah.
When would you know what to do with the change in the unit or put it in the work?
Just a regular KE formula?
Yes.
So in this problem, you have an initial velocity and you have a final velocity. And when you have two things that are changing with kinetic energy, you're most likely going to use work kinetic energy theorem when there's a delta, a change. You started with 1.5 meters per second velocity and you go to rest. Okay, so the change there is indicating that we're probably going to use that. In addition, you have friction, so some sort of energy loss is going to occur in the form of work.
And also, when would you use the one cosine theta?
We're going to see that right now. So let's go into that. So we start with our work kinetic energy theorem, which really tells us what is VF though, everybody? So I can drop that off already. Let's do that to make it easier. So my work kinetic energy theorem reduces to the following. Again, my work kinetic energy theorem tells me that the work done on an object is equal to the change in the object's kinetic energy, which is final minus initial. The final velocity happens to be 0, therefore that portion drops off. So this is the resulting work kinetic energy theorem. Now, Tristan, back to your question. If we know that friction is doing work on this body, we know it's the force of friction that is causing the work. So what was our work equation now? From 5-1, what was our work equation?
I forget. FD times D times cosine theta.
FD times cosine theta. Very good. Now, what kind of friction? What kind of force is this? Friction.
And you can plug.
Okay, so we'll call it FF.
Wait, can you just say that now? Can you just say that since there's force, you can just say that it's friction force?
Yeah, so you can put FF there. That's fine.
So what is normal force?
Well, in this problem, what's causing the object to slow down?
Oh, that makes sense.
Friction. We're going to replace friction, though. Do you want to take a break right now, or do you want to wait a little while? We're going to keep going. Do you want to take a break right now, or do you want to wait a little while? Can we finish this problem off? All right. Now, in this problem, the work being done is due to friction, so it's FF, the force of friction, times the distance the object is sliding. We're looking for D, remember, times cosine of theta. What is theta when it comes to friction, remember? What is theta? Good, Lisa, good memory. 180, because friction opposes motion. So the motion is this way, friction pushes back, the angle is 180. So we're going to have cosine of 180 there. We'll leave it for a moment. Okay, but keep that in the back of your mind. If you want to write at the top a given, you want to write this at the top right now, you can, just to remind yourself. It becomes a given. It wasn't obvious that that was a given in the beginning, though. Do you see what I'm saying? As you progress through the problem, you pick up on more parameters. You pick up on the fact that theta is now 180 because it's friction. Jim?
Going that way, the theta would be 0.
Remember, if the object was moving this way, then friction would be going that way. Friction always opposes motion.
It doesn't matter which direction.
Exactly. It doesn't matter which direction you're moving, as long as you know that friction goes the other way. Okay, so it's always, in the end, going to be 180 for friction. For sliding kinetic friction. I don't want to say that, because if you take college physics, you'll learn about rolling friction, and that helps you. So it's a little different. Now, let's keep moving. What is the force of friction defined as? What is the force of friction? Because we don't know what FF is. We're trying to solve for D, but we're not given what FF is in this problem. What is FF defined as?
MUFN.
Mu Fn. And we have mu. So there's a good chance we should plug that in to start. So let's go ahead and plug that in now. There's a Pokemon called Mew.
Yeah.
And you too.
Does it have to do with friction?
Yeah.
That'd be cool. No, right? Mew? Remind me, I thought of you guys twice this weekend. I gotta tell you both stories. Okay? After this problem, we'll talk about it. No, not in Pokemon. So this is our equation. Let me move it up so you can see it. I'll get rid of our givens. We'll come back to those. So here's our equation now. We replace FF with mu Fn. With mu Fn. Why did we do that? Because we're given mu. We're looking for D. We cannot find D in this equation right here because we didn't know FF. So we replace FF to make it easier. But now the problem is, what don't we know now? We don't know Fn now. We know mu K. We know theta. We know M. We know Vi. But we don't know this Fn and we don't know D. We're trying to find D, but we can't find D until we can replace Fn with its equivalent expression. How might we find Fn?
Would Fn be, wouldn't this Fn be mg?
Why?
Because the normal force has to counterweight is equal to the gravitation, the Fg.
When?
When there's a 0 in the y.
Yeah, when there's no other forces acting on an object, and an object is just moving horizontally and there's no pull or push or vertical motion at all. Remember that these two forces, Fn and Fg, are going to be equal and opposite. It's like right now, your desk is pushing down on the ground is pushing back up with the weight of the desk. This happens when there's no vertical motion, or there's no pull at an angle, or pull vertically. This push that we gave this person, or the person's momentum, is only horizontal. There's no vertical pull or push or force. So in this problem only, or in these scenarios again, which a lot of you guys use this on your test, and it wasn't true in some examples. You said, well, Fn is just mg. That's not true if I'm pulling on the object at an angle. Or it's not true if the object is moving vertically, or if it's on an inclined plane. Fn is not mg in those scenarios, but in this scenario, Fn is opposite of Fg. So as Tristan and Nick both mentioned, we can replace Fn with Fg because they're equal and opposite. But Fg is mg. So let's do this. Okay? Again, it's a lot of work what we're doing right now, so please try and bear with me. We look at our free body diagram to see that the normal force and the gravitational force balance each other out in this state of vertical equilibrium. And therefore, the normal force can be replaced with Fg. So if you have to write a little note down, you're welcome to do that. Just put a little Fg right here to tell yourself that that's what you're doing. You're replacing your Fn with Fg. But Fg, we have to always remember, is mg, mass times gravity. What is convenient in this problem? I'll say coincidental. It's not coincidental. Convenient. Yeah. Well, mass is given, but what happens in this problem? Yeah, the mass actually cancels. So, did the mass need to be given? Was the mass given? Yes, because I know some people might solve it numerically, but the masses end up canceling on both sides. Okay? Because they're all multiplications. So, for example, look at the left-hand side. It's mu k times m times g times d times cosine. It's all times. So how would you get rid of something that's times? You would divide by m. But if you divide by m on both sides, those m's drop off. Okay, so the masses end up canceling. What are we trying to solve for? D. Trying to find d, so let's solve for d. So solving for d, just move everything over to the other side.
So you just divide by mu cosine theta.
Mu k g cosine theta. Okay? Don't forget the g. I'll move it up so you can see better. Mu k g cosine theta. Divide by that whole term to get d by itself. And you could move around the negative 1/2 and put the 2 in the bottom and stuff, and that's fine. But I'm just going to leave it for the sake of simplicity. So again, we're taking this, taking g, we're taking cosine theta, dividing by all three of those to get d by itself. How do you divide by three things at once? Put them all in the denominator on the other side. Tristan, stop talking. The negative 1/2, the vi squared still remain. They remain here. Again, if you want to write this differently, you can. I'm going to leave it for the sake of the time. Okay, for the sake of this question. Let's plug in. Initial velocity was 3 meters per second? Is that, yes? 1.5. Okay, notice the negative on the top. Well, we're going to have cosine of 180 in the bottom. What is going to happen? Yeah, they're going to cancel out with the negative 1. What else do we know? The mu k is 0.25. G is 9.81. And this is cosine of 180. Okay, so remember, the negative 1 from the cosine 180 will cancel with the negative from the numerator, giving you a positive value for d, which is logical. You can't ever have a negative value for d. It's a distance traveled. It's a distance traveled. You're not going to have a negative value for d in these problems. Make sure you put parentheses around your denominator when you type this in your calculator. It absolutely does matter, because when you hit divide on your calculator, it will divide by 0.25, and then it will multiply by 9.81 and multiply by cosine 180 if you don't put a big parentheses around the whole thing. Okay? Order of operations, PEMDAS. So you need that bracket around that denominator, please, 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 please.
Would it make more sense just to solve for the numerator than write it down and solve for the denominator?
Or solve for the numerator. There's a button on your calculator called store. You can store that value.
Or you can solve for the numerator and then just hit divide and then it'll be the answer.
Yes. And then put that all in parentheses.
Yeah.
I personally would do that for sure. I would type in 1.5, well 1.5 squared is 2.25. Half of that would be 1.125. And then divide that by the quantity in the whole denominator, whatever it is. Numbers. What do we got?
I have 0.46.
That's what I got. Anybody else get 0.46? Okay.
I got 0.458715596.
Okay. So this would be to the nearest hundredth, which some of you really, didn't follow directions. There was one question on your test that said round to the nearest hundredth. Okay, that would be the hundredth. Doesn't mean that for the rest of the test you round everything to the nearest hundredth. Okay, the directions always say for the last part, round to the nearest tenth, round to the nearest tenth. But because it was mu, it's a very small value, I asked you to give more decimal spots for that reason. Okay, so make sure you follow directions on the test when you say rounding. So that means that this object, or this person would slide only a half a meter. A meter is about this big, a little more than 3 feet. So this person, if they ran with 1.5 meters per second, which is not fast, ready? Here's 1.5 meters per second. This is how fast 1.5 meters per second would be. Like walking quickly, like that. So imagine you're walking that fast, okay, and then you stop, and you slide on your socks. If the coefficient was 0.25, which is reasonable, you would slide about this far. Which makes sense. It's like running and then just coming to a sliding stop. That's the idea. Okay, you know what I thought of?
What?
Please tell Look at baseball.
No. What did I think of when I thought of running and sliding? Not interesting, but that could make sense. No, there's a movie. There's a movie, I forget what it is, but it's an old movie and it's a classic. I can't remember the name, but there's a scene where the guy comes out with a guitar and he's got his socks on and his shorts. I think it's
No, Guitar Hero.
what? What is it?
It was like the Guitar Hero.
It's a Guitar Hero commercial, like Alex Rodriguez.
No, but there's an old movie. It's I think it's Back to the Future.
That is Back
It's Back to the Future. Where Michael J. Fox comes out, Back to the Future, and he's playing his guitar, and he comes out, and he slides on his socks on a wooden floor.
Yeah.
He runs across and comes out sliding and playing the guitar on socks.
I feel like that's not.
Is something else or no?
I thought it was Tom.
There's
one with
Oh yeah.
because he's running in his white shirt.
Yeah, maybe it is. It's probably what movie is it though?
Top Gun.
It's not. Maybe it is Top Gun.
I don't think it's
Anyway, that's what made me think of this problem.
Alice in Wonderland.
All right, so the idea of an object that has energy based on its position, its shape, or its condition. So, for example, you guys have heard about potential energy as in an object raises to a certain height, it could fall, it has potential energy and height. And that's what we'll talk about in a moment with gravitational potential energy. But the idea of potential energy is the potential to do something, right? So, if I took a slingshot and I pulled back on the slingshot, I am storing energy where? Where am I storing the energy?
In your arm.
Well, my arm is creating some sort of energy.
In the stretching of the string.
Yeah, the material, sure, string or rubber, whatever it would be. But the actual rubber band, the material, the string that you would pull back on, when you pull back on that, you're storing energy in there. And when you let go, that energy is then pulling it forward and converting it into kinetic energy, causing it to move. So the idea of potential energy is not just gravitational at a certain height. We are going to specifically look at that and spring energy both. Okay, so let's take a look at gravitational first. Gravitational potential energy is due to the position of an object and caused by gravitational fields. So for example, when I stand up on this chair, I have gravitational potential energy because if I step off the chair, what's going to happen?
You're gonna fall.
I'm going to fall.
I'll catch you.
So I have the potential to change my motion based on my height. So if I were to fall, it's going to change my motion, so you have the potential for something to change. That's gravitational because it's based on your height. If I'm on the ground right now, I have no potential energy compared to the ground. But if suddenly I was on the ground and the floor fell out below me, like the floor just like it was a trap door, and the trap door just opened, I would now have potential energy causing me to do what? Fall down. So it's all relative to where you're at. So right now I have no potential energy compared to the ground. Okay? But the minute I'm on a chair, I step on a chair, I have potential energy compared to the ground. But when I'm on the chair, I've got no potential energy compared to the chair. You know, it's weird to think about. But if I'm on the chair, standing up on a chair, and I'm not moving, I'm just standing here, I have no potential energy compared to the chair. Because if I just stand here, nothing's going to happen. But compared to the ground, I do have potential energy. Same thing with the desk. If you stand at the desk, you have potential energy compared to the chair and the ground. So the minute there's a height differential, potential energy exists. Okay, and it's all based on a relative baseline. So if I consider the floor to be the ground, then everything above the floor has potential energy. If I consider this desk to be the ground level, then this has potential energy, but the object sitting on the desk has no potential energy compared to the desk. But compared to the ground, it does have potential energy. So again, it's all relative. So let's look at our diagram here. In our diagram, we're going to see that the object starts at position A, well that's what it's trying to indicate. It bounces off, it's going to hit position B, and then continue to bounce down. So up at position A, it's got potential energy compared to B and C, because it's above that level. It's got a certain amount. So we are going to be looking at the change in height. So see this formula here? If you would like to, you can put a delta in front of the y. You can write mg delta y. You're welcome to write mg delta y, because it's the change in height that matters. And you should really write that down. The change in height. The change in height. Okay, just like in the problems we had y equals vit plus 1/2 at squared. We would use that to find the height of a cliff. Well, we're really finding the change in height from the top of the cliff to the ground. That's what we're finding, the delta y. Just like here, we're looking at the change in height, delta y. The mass is obviously the mass of the object, and g is the gravitational constant. Okay, let's take a look quickly at our units. It's energy, just like kinetic energy. So what do you think the units are going to be? Joules. Let's prove that. Units of mass are kilograms. Units of g are meters per second squared. That's acceleration. Units for y are in meters. And again, just like earlier. Earlier we had kilogram, meter squared per second squared. Same thing. This becomes kilogram, meter, which is meter squared, per second squared. So again, our units are joules. Our units are joules for energy. Okay, this is gravitational potential energy. Let's take a look at our next example. A 40 kilogram object is raised from the bottom of a well using a pulley system. So you've got a pulley, you're lifting up, object moves out of the well. The depth of the well is 25 meters and the object is raised 3 meters above ground level. Determine the change in potential energy of the object. The change in potential energy of the object. So in these examples, it might be useful to draw a diagram. So here's your well. Here's the lip of the well. Okay, here's the object at the bottom of the well. It gets lifted up until it's about 3 meters above ground level. So here's ground level. Let's draw ground level. Okay, it gets lifted up until it's about 3 meters above. So in this problem, if we think back to our formula we just looked at a moment ago, we have PE is equal to mgy. What should I consider to be zero energy in this problem? What's the lowest possible height in this problem? Where is it? In words, tell me.
The bottom of the well.
The bottom of the well. So let's call this like our starting point. Let's call that our zero reference point. So what would the red line be then? What would the height of the red line be? 25 meters. How come?
Because that is how deep it is.
The well is
25.
good. The well is 25 meters deep. So from the top of the well to the ground level, which is clearly not right, it's a little bit off, so please fix that on yours. To the ground level, from the ground level to the bottom of the well here at the bottom is 25 meters. Now we go an additional how many meters out of the well? 3 meters. So what would this level be then?
28.
So my delta y in this problem is 28. Again, you think of the starting point and the final point. The starting point and the final point. YF is 28, YI is 0 in essence. So how far have you gone? You've gone 28 meters upward. So delta y, or in the equation if I look, y is 28 meters. That's one of our givens. The mass is given as 40 kilograms, and at this point you can just plug in. G is known. What is G again?
9.81.
Yeah, 9.81. Oops, let me get the right number first. Okay, so we've got 40 kilograms times 9.81 meters per second squared times the change in height, which is 28 meters upward. What if the person dropped a pebble back into the well? What's delta generically? Instead of being positive 28, what would delta be if I dropped it into the well?
Negative 20.
Yeah, y would be negative something, whatever the height initially was. Okay? So remember, if you move upward, your y is positive, just like kinematic motion. No different from kinematics, 1 and 2 dimensional.
The answer?
Sure, we got it.
10,987.
Okay, I'll put the nearest joule just in this example because it's such a large quantity. Agree, disagree? Agree? You concur? Have you seen Catch Me If You Can?
Yeah, that's what I was thinking.
With Leonardo DiCaprio? Why did you concur? Why did I concur?
Well, I like that.
It's very good. It's funny. It's intriguing, really. Okay? So again, the change in potential energy, the change is 10,000 joules. So this object, you could say, has gained 10,000 joules of energy. But you know what? Now suddenly, I take the object out of the well. Okay? I take the object out of the well, and I place it on the ground on the grass. I place it on the grass, and it's sitting there at rest. You would then probably say it's got no more potential energy, because now you're like starting the problem over. Now the grass is your zero line. So the object comes out of the well, and the person decides to place it on the ground. So here's the well. Here's let's say the grass. I know it's not blue, obviously. Okay, here's the grass, and here's the person standing right here. Okay, there's the person standing there. Now, they take the object and they place the object on the ground next to them. Most likely you would say something like, now it's got no more potential energy because it's resting on the ground. But again, what that means is now you're considering the ground level to be your zero line. Whereas in the beginning of the problem, we considered the bottom of the well to be the zero line. Okay, this is just an extension of the problem, so you can think about this conceptually. This is where your part 2 kind of problems come from. Okay? How would that have zero energy suddenly? It's like if you call the ground now the baseline. And you put this on the ground, well, it's got zero height, so y would be 0. Okay? So we're partitioning the problem again. Remember how you're studying piecewise functions in math? We talk about piecewise functions in kinematics. We've done that. Where the object moves to the top, it pauses, and then it moves back down. We did those examples, and in those examples, guys, we looked at the first part of the problem and the second part of the problem. Okay, so the same idea holds true here. The last thing I want to talk about today, I want to do one more example. And can I get a reader for this one? Can I get a reader for this one, please?
An ant's potential energy keeps changing since it is constantly walking up and down hills and carrying heavy pieces of food that vary its overall mass. At instant A,
Guys, stop.
it is carrying 3.5 times its mass in addition to its normal mass, and it is at half the height of that at instant B, where it is not carrying food. At which instant does the ant have more potential energy? By what factor?
So it's really confusing if we don't draw a diagram here for sure. So let's start with that. So let's draw an ant. Here's our ant, little box. And it's going to move up a hill and end up here at some point. And we're told that at instant A, here's instant A, it's carrying 3.5 times its mass, which is true. Ants can carry up to 6 times their mass, which is crazy to think about. Imagine walking around with like 1,000 pounds on your shoulders. That's pretty much what ants do, okay? Relative to your body weight. So, Imagine, I know. Imagine. Ender's Game. Ender's Game. The buggers.
Oh, really?
Yes.
Yeah.
I'll make another step for that. Now, the mass at instant A would be 3.5 times its mass. 3.5 times its mass in addition to its normal mass. So let's call the mass of this ant M. So the mass here would be 3.5 m plus m. Again, 3.5 times its mass, 3.5 m, in addition to its normal mass plus m. That's the mass at that location. Okay, we don't have a number. We know that the mass of the ant is m, and it's carrying food. At the higher height, it is at half the height. Oops. It's at half the height, so it goes down. Let's go down instead. I apologize. Let's go down and draw the ant down here. Doesn't really matter, okay? But for the sake of this problem, let's do it. So at instant B, it's at half of the height. And we know that it is not carrying any food now. So the ant is moving along by itself. So what is the mass then? What could we just say? Just m. Very good, Lise. Just m. Now, if we know the mass at both heights, and we know the relative heights, what could I call the height initially? We don't have numbers. Again, no numbers for these problems. What do you call it? Call it y, some quantity, right? Some variable. So if at the first location it's y, what would the height be at the second location?
1/2 y.
Why is it 1/2 y?
Because it says half the height of that at instant B.
Yeah. At instant B, we're at half the height now. We're at half the height. So in the first scenario, call this height y. I'll put it in red so we can see the difference. In the second scenario, it's half of that height, so 1/2 y. Now, these problems are not asking for you to come up with an amount of energy. What does it say? Not an amount of energy. Yeah, which is greater? Which is greater? So we're looking at a relative energy. So if I knew the energy at one instance was, and imagine it's not an amount. Say the energy in one instance was mg, and the energy in the other instance was 2 mg. The second instance has twice the energy of the first instance. So it's all in terms of variables. So what was our equation for potential energy from the last slide? What was our equation for potential energy? Potential energy, Lou.
Change in y and g.
Yeah, so mg delta y. Well, in the first scenario, what is the actual mass? What is the actual mass? 4.5 m. Okay, so in the first scenario, we have 4.5 m. Okay, that's the mass. Right here, 3.5 m plus a single m gives us 4.5 m. Times g, the gravitational constant, times the height. Well, what's the height in the first scenario? What did you call it, Nick?
Y.
Yeah, we just called the height y. So this is the amount of energy in the first scenario. Again, it's not a number. It's not a number, and that's fine because we're not looking at numbers here. But in the second scenario now, we've got a different setup. We've got the mass at the bottom, m. We've got g still, and now we've got half y. We've got half y. Oh, Lord. I need to pause because I made a mistake. I had it right the first time. Switch your y's up. Let's read the question again. I misread it the second time. At instant A, the first instant, it's carrying 3.5 times its mass, and it's at a height that's half of instant B. So remember the original diagram that I drew? It was correct, and I'm trying to figure out why I changed that, okay? So just switch them up. Okay? Yeah, I saw half the height and I saw instant B, and initially my brain put those two things together and made that half the height. But it says that A is half the height of B. So switch those up, please. So let's go ahead and call this 1/2 y, and erase this 1/2 down at the bottom. So that changes up here. Okay, right here, instead of y, we're going to put 1/2 y in for that. So this is an ant carrying uphill. Okay, so again, this is going uphill. going uphill. So at this height, when the ant is uphill, it's got a height of y and a mass of m. When it's down here, it's half the height, but the mass is 4.5 times the normal mass. So for m, we plug in 4.5 m for the original condition at A, but the height is half of the original height. At point B, the mass is just m, the height is just y, so at point B, it's just mgy. Which of these quantities is greater? Is the quantity at point A, right here, greater than the quantity at point B, or is B greater than the quantity at point A? And how do you know? And how do you know?
Well, could you plug in? Can you just make up numbers then?
You could, but without making up numbers.
Oh, I think the first one, point A is greater.
Point A is greater, why?
Well, because I just kind of took 1/2 of 4.5.
And it becomes?
2.25, right?
So everybody see what Nick is doing here? He's saying there's a half, there's a 4.5, so he brings out the numbers in front, and what's left? Once you get rid of these numbers, cover them up. You're left with mgy. Again, move the numbers out in front, you're left with mgy. So the energy here, at the lower level, believe it or not, it has more potential energy at the lower level, which is misleading at first. Because you think as you go up further, higher up, you gain potential energy. But what did the ant lose on the way up the hill? Yeah, he lost mass. The ant dropped the piece of food that he was carrying on the way up the hill. So although he started at a lower level, his or her, depending on ants, if they have a genus or a gender, the ant has a certain amount of potential energy initially, 2.25 mgy. At the top, the energy of the ant is only mgy. So see the second part, by what factor? Is it greater? What's the factor that you're seeing? 2.25 is the factor. So we could say, as a conclusion statement for this problem, that the ant has more potential energy initially, or at point A. And by what factor? The factor is 2.25 times bigger than at point B. And I wanted to show you this because if you lose mass, even as you gain height, okay, your energy can actually go down. It can go down. For your practice for the next 2 days, here's what you should do. Potential energy, but remember last class we talked about gravitational, which had to do with the location of an object. If an object is on a table, it's got potential to fall. It's got potential energy with respect to the ground. You right now have potential energy with respect to the outside ground, like the street, because you're at an elevation of 4 floors up. So you have potential energy based on your location. Now we're going to talk about potential energy based on a stored energy in a spring, okay, which is one of the most useful and versatile things you can ever learn is springs. And I know that sounds kind of crazy, but almost anything in the world can be modeled by springs. Because of the simple fact that a lot of things vibrate at very high frequencies you don't even notice. So we were talking about last class how if I was standing still, I don't have any kinetic energy because we're looking at a macroscopic level. But if you look at your particles and your molecules in your body, everything is vibrating. There's some motion between the molecules. So springs are widely used on a microscopic level and, as we're going to see, on a macroscopic level in class. A really good application of springs, and I'll talk more about this when we learn more about it, but BMW, about, I think it was like 10 years ago, had a problem with one of their models of their cars, and the right passenger door, where the passenger would sit next to the driver, would vibrate uncontrollably after like 60 miles an hour, and it would start to shake. And after like, I think it was 60 or 65, whatever it was, the car door would start to shake at a certain range, but then once you got above 70, it would stop shaking. But obviously you don't want your door to be like shaking as you're driving, right? So what they ended up using were springs. And they attached many springs on there and modeled it, looked at the vibrations of each spring to model it, and they used a matrix to actually figure out how they can dampen the spring effect or dampen the vibrations. So even though we're not going to maybe do exactly that, we're going to talk about that, we're going to talk about vibrations, but springs are widely used. You're going to see them a lot in science and engineering. Okay, so what we're going to talk about today is spring energy. What do I mean by spring energy? Spring energy. How can a spring have energy? Think, use common sense. How can a spring have energy? James?
If it's under tension, then it wants, it's
Desires.
It's exerting force on whatever's holding it.
Good. So if you pull on a spring, it pulls
That.
back towards you. That's exactly right. So when you pull on a spring, it has the potential when you let go to do what? To move, to compress. So that idea is that you're storing energy in the spring. Another example, as opposed to tension, is what? What's the opposite of tension? It's the word that means opposite of tension. Opposite of tension.
Compress.
Compression. Good. Compress. Compression. Take a spring, okay? Take a spring like in a pinball machine. When you use a pinball machine, you pull back on the little handle, right? It compresses the spring. And then when you release, the spring hits the pinball and starts the game. Okay? That's how a pinball machine starts. You pull back on the lever, the spring compresses, you let go, the spring expands. So it's like a launch pad if you think about it. If you had a spring compressed, and you could somehow put like a pin through it to hold it compressed, you put an object on it, and then you pull the pin, what will happen? The spring will expand and it will launch the object. So a simple example of like some sort of an object being launched. Doesn't have any specific application, but like, remember we talked about catapults? We're going to look at catapults and look at the spring energy that launches the object forward. So our formula here, and I'm putting an S there. What does the S probably stand for? Spring. Okay, so potential energy in a spring. You could also think of that as stored. Some people are like, oh, stored energy, but you could have other types of stored energy as well, like internal or chemical energy. So we'll say spring. And it's 1/2 kx squared. Now, we have to talk about what these mean. K, the variable K here in this problem has to do with what's called the spring's rigidity or stiffness. Spring stiffness or spring rigidity. Okay, so a stronger or weaker spring. Okay, or rigidity. Shh. Or rigidity. Now, a spring in your pen, just to give you an idea, is a very low K value because the spring in your pen is very weak. If you ever take your pen apart, take that little spring out that's in there, you could sit there and you could distort that spring permanently. You could pull enough and it would break. It would be a permanent deformation. It's not a strong spring, so it would have a low K value. But the springs that are in your car and your hydraulics, between the chassis of the car and the actual axle that help the car from not doing this when you're driving to minimize the vibrations, those springs are very high K values. They're larger diameter. They're larger cross-section. They're different material. There are more coils or less coils. So the K value of a spring has to do with actually many things regarding the spring. We're not going to go into detail as to what they are, but we want to look holistically at what the K value is for objects. So you could say that a spring on a bike, like a bicycle, the little springs that are there, the shocks, you call them, they're springs really. Those shocks are like a medium K value. A larger K value would be springs that are on like a car or a big, say, machinery in some sort of a plant. So some sort of manufacturing plant, the machinery there that they're using probably involves large springs in order to minimize the vibrations of the machine. Okay, there's probably also very small springs in different locations. Now, again, as K goes up, what's going to happen to the potential energy in this problem? Look at your formula here. If K was 5, and then suddenly I have another spring with everything else the same, but K is 10. If I double the K value, what happens to PE? What happens to PE?
Goes up.
Yeah, it goes up by how much?
What happened? Double.
Double. 2. Sorry, you went the other way. So it doubles. So if I have a spring that's twice as strong as another spring, and I'm able to compress them the same distances, the stronger spring has twice as much energy stored. Again, exact same scenario, 2 springs, everything's the same about them except the K value, same length, everything. You compress them both the exact same distance. This one that has a double K value will have double the energy because K is directly related to potential energy. Okay? As K goes up, potential energy in a spring goes up. That's our relationship for this one. How about the X there? What do you think X may be in these problems? And I'll tell you now, it's not necessarily just displacement. It's something else for this. Something else. What may X be? Tristan? Yeah, how far or how far you pull or push. How far you extend or compress the spring. So let's look at a quick example. Not example mathematically, but an example of a diagram. Here's the spring. Here's how you model springs, by the way. You want to start drawing them. You draw a line, you draw a little squiggly, and then you put this dot at the end to show that's where the mass or an object would attach to the spring. James?
Is the K value of the spring the same irrespective of whether it's compressed or?
Yeah. Yep. So if it's compressed or in tension, either one, it's the same K value. Now, there are certain other things though, James, that we have to consider. Like, for example, and this is a really good question. What do you think? If you push a spring together and you keep pushing it together, you'll reach a maximum allowable push. It'll stop at some point, right? But if you pull in tension, what will happen if you pull too hard?
I mean, it'll deform.
It'll deform permanently. The spring will not come back to its shape. It has a tensile strength. And after that tensile strength is exceeded, it undergoes permanent deformation. So the stress that's applied to the spring is too much for its body, and it eventually will stretch. Take a slinky and pull it hard enough. It's not going to go back to the way it was, right? You'll permanently deform it. But if you push together enough, it's not really going to go. I mean, if you put enough force, I guess you would break it if you push together. But when you push together, you have like a limiting factor. You can't compress it any more than its actual size. But when you pull, you can undergo permanent deformation very easily. Okay? But same K value for each direction. Now let's say that this is the spring normally, okay, in blue here, and I take the same spring and I compress it so that now it looks like this, and I'll overwrite it. Same spring, but it's been compressed so that it's that small now. So I've pushed it, and I've taken, and I've put a force to the left pushing it. Okay? In this problem, what would X be? What would X be in this diagram? How could you denote what X would be? And this is in the formula we're looking at from a minute ago. And Tristan already said it has to do with how far it is compressed or stretched. So what would X be in this diagram? How could you denote it on the diagram? How far is this spring compressed or pulled apart? What's the distance that it has been compressed? And notice it doesn't matter if it's negative or positive because you're going to square X in these problems. What would the distance or displacement be that the spring has been compressed in this kind of a problem? What's that? Yeah, between the 2 points or the 2 dots. Very good. This is X in these problems. So make sure you write this down. Please make sure you write this whole thing down here. This is important. So X is the compression distance or the compression length. Okay? Compression distance or compression length. So technically we could say it's like a delta X. Okay, it's like a delta X. In engineering, we call something that is not being compressed, it's free length. So the blue, if you want to write this down, the blue diagram on the board right here is the free length of the spring. You're going to hear that term in your book, so you probably should write it down. The blue is the free length, and the red is the compressed length. The difference between the free length and the compressed length is X. Again, the free length and the compressed length, the difference, if you subtract those numbers, is what gives you X. So if I knew that the free length was 7 centimeters and the compressed length was 4 centimeters, X is simply 3, right? 7 and 4, 3 there, guys. So 3 centimeters for this one. Again, X is the difference between the free length and the compressed length. Okay?
So is the free length like 0?
It's like the equilibrium position.
Yeah.
Exactly. Exactly right. When a spring is at its free length, there's no forces applied, it's in equilibrium. When it's being pushed together, it's no longer going to be in equilibrium because you're pushing with a force and you're accelerating it so that it compresses. So again, free length minus compressed length gives you X for this equation. Is that clear? All right. I'm not going to go into the units just for the sake of time because I know we're going to run out right now. So I don't want to go into this. But your units overall are still energy. So the units are going to be joules. Okay, you're going to have K value. Oh, I should talk about the K units. K units are in newtons per meter. And I'll explain how this works. So just write this down somewhere. The units of K are newtons per meter. If a K value is 10 newtons per meter, or 10, but we're saying again, newtons per meter, the units. That means the following. It takes 10 newtons to compress that spring 1 meter. Again, if the K value is 10, it takes 10 newtons to compress the spring 1 meter. 10 newtons of force, so you know the amount of force it takes to compress it 1 meter. That's what K really means in essence. So as K goes up, it means it takes more force to compress that spring. So it's a stronger spring. That's what we said a minute ago. When K goes up, we have stronger springs. So a K value of 500, like on a car, means 500 newtons of force are required for it to compress a full meter. Okay? On a big scale, you're not going to compress things a full meter, right? So although it's in newtons per meter, a lot of the time your compression length would be given in like centimeters. Okay? Because smaller compressions, you're not going to be looking at things that are compressed by meters.
So it's always gonna be centimeters?
No, I'm saying traditionally you're going to see that your compression distances are going to be other units. Not always, no.
Still have to convert it to a decimal.
Yeah. So still in meters. So you'd have to convert this x, instead of 3 centimeters, that'd be 0.03 meters. So you don't have to convert the free length and the other length, just subtract and then convert afterward. Instead of doing 2 conversions and then subtracting them, subtract them first and then just convert. Okay? All right, let's take a look at an example. Oh, this is the diagram, sorry, that I just drew. Okay? So again, free length is out here. Compressed length is here. Distance compressed along the top. This is your delta x, or this is your x right here. Okay? That's what we were just mentioning a moment ago. Example 5, a spring is compressed a distance from its free length of 2 meters to a length of 0.5 meters. If the rigidity of the spring is represented by a stiffness of 50 newtons per meter, then how much, God bless you, potential energy is stored in the spring? Let's start givens. What's our givens? What do you know from the first sentence? From the first sentence, you have a free length of what? 2 meters. So we could say, if you want to, and this is, you don't have to write it this way, but if you'd like to, x free is 2 meters. Okay, and it's compressed to a distance of 0.5, so we could say x compressed. But you don't need these subscripts. If you want to just do the math ahead of time, you could list that instead. So you could have just, instead of listing this, just said the following. Okay, you could list this as your given instead. You're welcome to do that if you notice right away. Again, if you have the free length and you have the compressed length of the spring, subtract the 2 to get the x we're going to use in our formula. So you don't need to write these 2 as givens on the left-hand side unless you would like to. You're more than welcome to, though. It might help. Next, we're told that the spring stiffness is 50 newtons per meter. What variable is that? What variable is that? K. And we can tell by the units, newtons per meter are the units. So that's the K value. Now let's take a look at this. If we plug this into our formula, and I'm going to carry the units down so you can see this. Potential energy in a spring, 1/2 K times x squared. What you're going to get, and you're going to notice if you look at your units here, this is newton per meter, this is meter squared. So one of these meters is going to cancel with this meter down here, leaving behind newtons times meters, which is the same thing we had for work, and that's where the joules come into play. Okay, that's where joules come into play. So let's take a look at our answer here if we go through it. Okay, 1/2 of 50 newtons per meter times 2.25 meters squared. Again, I squared 1.5 to give me 2.25 there. I did this just to show you the units. That's the only reason I'm going through this. This meter here, I could use red. This meter down here cancels with one of these meters up here, getting rid of that squared for the meter term. Leaving behind newton times meter. And that's, again, what a joule is. Think back to work. Work was FD cosine theta. F was newton, D was meter. Again, we have newton times meter. So this is indeed joules. We can multiply 1/2 of 50 is 25. 25 times 2.25, 56.25. And my units are joules, amount of energy stored. Okay, amount of energy stored. Now, what I want to do is carry this right into section 5.3 now. Okay, that was the last thing I wanted to go over from 5.2. I want to go right into 5.3. And we might only get through the intro, but I want to begin it because we're on a bit of a tight schedule with the junior retreat the next 2 days. So over the weekend, you should definitely finish all of 5.2. Okay? And if you'd like to be a little bit, what's the word? Get ahead? What's the word I'm looking for? Proactive? Proactive. I'm trying to think of an adjective. If you'd like to be a little proactive, Over the weekend, you're welcome to look at 5-1 and 5-2 problem sets because you can definitely start those. Okay? Definitely be proactive. Anybody know the next test on their schedule? 25th? Your birthday, huh? Sorry. 25th.
Isn't that like Thanksgiving?
Thanksgiving is that Thursday. So we have the test on Monday the 25th. We have school on Tuesday. We have Wednesday, I think something else.
I don't think we have school on
School and mass? Or? We do have something Wednesday, yeah.
Wait, is this the next one that was?
Hey guys, which one wasn't on the actual page? Who can tell me?
Oh no, I went to 72.
172.
There were no questions on
Yeah, no, it
172?
was 174.
Or
No,
was it 171?
there is no questions on 172.
Alright, so I'll check into this. I'll check into it.